In this video, we're going to look at the unit cell and basic crystal structures. So inside of a crystal, the atoms that are in a crystalline structure are in a repeated pattern. Now, the basic unit of this repeating pattern we call the unit cell. So let's imagine this image on the bottom left is our crystal, and this purple square is our unit cell, and it's just replaced over and over and over and over again. It's like tiles on a floor. One tile is your unit cell, and all the tiles together on your floor would make the crystal in that example. And the way you talk about unit cells is that you talk about their geometry, so cubic, tetragonal, orthorhombic, rhombohedral. So don't worry about memorizing these, but that's how you would tell your different unit cells from each other. And note that each of these unit cells, for the most part, are going to be exactly the same as its neighbors. It is possible that one unit cell could be slightly different than another. You actually see that in biochemistry. But here, we're just going to think of the simple case where they're not going to be different. So let's look at the different types of simple unit cells we can have. And we're going to start with the simple cube. In the simple cube, we have a cube, and at each corner, we have an atom. And these atoms are touching their neighbors right along the edge. So each atom goes halfway across the box. So if the radius of the atom is r, the length of our cube equals 2r. And each unit cell in the simple cube contains exactly one atom, which might be hard to see from this picture, but for each one of these atoms, only 1/8 of the atoms actually in our cube. So 1/8 of an atom's in our cube times 8 atoms equals exactly 1 atom. And here's that representation with everything not in our cube chopped off, and this is trying to show you 1/8 of an atom's in our cube. So when we talk about unit cells, we're going to be talking about coordination number and packing efficiency. Coordination number is just a number of atoms with each atom is in direct contact, not each atom, which each atom is in direct contact. And the packing efficiency is the percentage of the volume of the unit cell occupied by space, or the spheres. So not empty space. How much of this cell is taken up by our atoms? And generally, the higher the coordination number, the greater the packing efficiency. And we calculate packing efficiency by taking the volume of our atom divided by the volume of our unit cell times 100. So let's go on to a different types of basic cell, our unit cell, and that's our body-centered cubic unit cell. It's like the unit cell we were looking at the previous slide, where you have 8 atoms at each corner, but this time you have an atom in the center as well. And what's also different is that the atoms at the corners aren't touching each other anymore, but you are touching the center atom. So you're touching on a diagonal, which means the length is equal to 4 pi divided by the square root of 3. That is the length of each one of these cubes. This contains 2 atoms per unit cell, because again you have the 1/8 atom from the corners, and you have a whole atom in the center that's not shared, so that whole atom's in one unit cell. Here our packing efficiency is 68%. Then you have the face-centered cubic unit cell, where again you have one atom at each corner, but this time you also have an atom dead center on one of your faces. And even though these atoms are colored differently, these are the same atoms or molecules. Here, atoms do not touch on the sides of the cubes again, but they do touch along the face of the diagonal. As you can see, the purple and the gold or yellow here are touching. Here, the length of our edge is 2 multiplied by the square root of 2r, where r is our radius. here we have the most atoms packed in compared to all the unit cells we have seen. We have a total of 4 atoms per unit cell. Again, we have 8 atoms on the corner, so 1/8 of that atom's in this box. Then we have an atom on each face. Half the atom is in the box. And since we have 6 faces, like a die, and half the atom's in there, 1/2 times 6 equals 3, plus our 1 from the atom in the corner equals 4 total atoms with a packing efficiency of 74%. Now, there are also efficient ways that we can pack our atoms in this crystal. So not just thinking about the unit cell here, now we're thinking about the overall geometry. Right? And the way to think about our closest pack structures is to imagine fruit in a grocery store that's stacked into layers. So imagine you go to a fruit aisle and they have oranges packed. And when you see the oranges packed, you'll see that they do it in such a way that they're all offset by a half. So here we have our oranges, our atoms packed. Our next layer is offset by a half. Our next layer is offset by a half, so on and so forth. This allows us to pack more fruit into our display, or in this case, more atoms into our crystal. And you can further increase the amount of atoms you can get into a crystal by not only having them layered like this in one layer, but if you have 2 layers, these again, the 2 layers can be offset, and this will increase your packing efficiency. So by doing an offset packing of atoms like this, we can get our packing efficiency up to 74% and a coordination number of 12. Now for these closest packing unit cells, there are 2 different types we're going to look at. First is hexagonal closest packing. And here we have a pattern of A, B, A, B. So layer of A, then B, then A. And keep in mind, these are all the same atoms again. We're just arranging them differently in different layers. So for example, 3, 7, 3. Here our center atoms actually touching 6 atoms, 3 from above and 3 for the bottom. And our cell is going to look like this. So here's a layer of A, and surrounded by each side is our layer of B. And compare that with cubic closest packing, which looks very similar. The only difference is that layers C and A are now rotated 180 degrees. In our hexagonal, both layer A and C were arranged in the same direction. Cubic, they're just arranged 180 degrees. That's the only difference. So for here in this example, layer A would look the same as B, C, D, and then E. So 4 layers away from it, you have your repeating pattern. And so this is what it looks like. 1, 2, 3, 4. We have all of our layers packed in there. And this again will allow us to get some efficient packing. And that's it for this video. I will see you in the next one.